Which regular shapes can you draw perfectly between the points of a 3D grid? Well, I mean, we can draw a square, but what's more interesting is that we can also draw an equilateral triangle. And taking 6 copies of this triangle gives rise to a regular hexagon. In fact, we can draw both of these shapes on a very special kind of 2D grid. All we need is a slight change in perspective. A few videos ago, we found out that, somewhat surprisingly, the only regular polygon you can draw on a standard square grid is, well, a square. And that understandably raises the question, well, what about other grids? Can we find a grid which lets us draw any particular regular polygon? For example, does there exist some special grid which lets us draw a regular pentagon? I mean, there are lots of other shapes other than squares which can tile the plane. And for that matter of fact, why restrict ourselves to just 2 dimensions? Just so we're all on the same page, let's quickly go through the argument we found at the end of the last video. We first assumed that you could draw some regular n-gon with its vertices on a square grid. Then we found a process to generate a strictly smaller regular n-gon, which must also have its vertices on the grid. In this case, we rotated each vertex 90 degrees about the neighbouring vertex. And this process could be repeated indefinitely. However, in a finite space, there can only be a finite number of these grid points. So we have a contradiction. Our original n-gon with its vertices at lattice points couldn't have existed. This argument doesn't quite work with the equilateral triangle. They in fact get bigger at each step, not smaller. But it turns out that the equilateral triangle is constructible if and only if the regular hexagon is constructible. And we just eliminated the regular hexagon. Now, the key idea I wanted to get to is that this process of finding transformations which leave the grid invariant but generate strictly smaller shapes grants us a lot of creativity when looking for a proof by contradiction. The most asked question on the previous video was about which regular shapes can be drawn on triangular and hexagonal grids. We have a lot of 60 and 120 degree angles floating around, so as you might have guessed, we can draw an equilateral triangle and a regular hexagon on both of these grids. But are there any other regular polygons? Well, let's start off small. Why don't we assume that we can draw a square on one of these grids? On the square grid, 90 degree rotations left the grid invariant. And there's a very similar analogue for triangular and hexagonal grids. Here, 120 degree rotations leave both of these grids invariant. Unfortunately, a single 120 degree rotation doesn't generate a smaller square. But what if we chain 2 of these together? In the second 120 degree rotation, we can rotate about a different point. And now look! One of these vertices has been mapped inside of our starting square. We can repeat this process on all 4 of the vertices of our starting square, and by symmetry we've generated a strictly smaller square, which must also be contained on our triangular or hexagonal grid. And just as before, this process can be repeated indefinitely. But there are only finitely many grid points in a finite space. And we have our contradiction. What's great about this argument is that it doesn't just work for the square, it also works for the regular pentagon. And when dealing with regular shapes with 7 or more sides, well, the task becomes even easier. Their interior angles are all greater than 120 degrees, So we can just apply standard single 120-degree rotations to generate a strictly smaller regular n-gon. Finally, just as a sanity check, we should see where these arguments fail for equilateral triangles and regular hexagons. And instead of getting smaller shapes, we end up in these repeating cycles, so there's no contradiction to be had. Now we've handled triangular and hexagonal grids, so what other grids could we consider? Well, let's take a closer look at the triangular grid. If I hide all the lines and just leave the points, then something interesting happens. We would get the exact same set of grid points if we tiled the plane with these rhombuses. Maybe we could consider grids involving any rhombus? And for a matter of fact, we could generalize even further to grids made up from parallelograms. Now, not only do we have infinitely many points, but we have an infinite family of grids with multiple degrees of freedom. Surely now we can find some other regular polygons. I'd encourage you to pause and give it a go. Did you find anything? No? Well, neither did I. Maybe finding regular shapes other than hexagons, triangles and squares is just inherently impossible. Now, you know the drill. Let's assume we can draw some regular n-gon on a grid of parallelograms and try to find a contradiction. Rotations seemed to work before, so why not try that again? Well, here's the first hurdle. For the vast majority of these grids, there aren't any rotations smaller than 180 degrees, which leave the grid invariant. That means we need to consider a different kind of transformation. Well, translations don't seem very useful. It's not exactly clear how we'd find a strictly smaller regular n-gon using translations. I'd encourage you to pause and try to find another transformation which leaves the grid invariant. Well, given that we have a grid of parallelograms, maybe we can use this to generate a transformation. For any 3 points on this grid, is it true that the fourth point which forms a parallelogram with the first 3 is also on this grid? I mean, intuitively, this feels like it should be true. And indeed, it is true. Because any of these 3 line segments are between 2 grid points, if we translate a line segment, it will also land between 2 grid points. This is a rather creative transformation, but it's the key to solving the problem. Look what happens if we apply this transformation to each triplet of consecutive vertices of a regular pentagon. We've generated a strictly smaller regular pentagon, which must also have its vertices at lattice points. And I'm sure you're getting sick of me saying it, but this process can be repeated infinitely many times, so we have a contradiction. This exact argument works with heptagons, octagons, and so on for all regular polygons with 7 or more sides, because one of the angles in the parallelogram is greater than twice the other angle. And when all is said and done, that just leaves us with 3 familiar shapes: the equilateral triangle, the square, and the regular hexagon. If we apply this inwards parallelogram argument to any of these shapes, they all, thankfully, fail in their own unique way. Now that we've solved the problem for an uncountably infinite number of 2D grids, it's finally time to jump up into 3D. Let's start off simple with just the 3D lattice of cubes. At the start of the video, I showed that you can draw equilateral triangles and regular hexagons alongside the obvious squares. So, time to ask the age-old question, are there any other regular polygons? Well, first, I just want you to take a careful look at this 3D lattice. Like, really squint and look at it closely. Maybe just try focusing on a single 2D slice. Look familiar? What if I overlay a certain grid on top of it? They look eerily similar, don't they? The 3D problem and the 2D parallelogram problem can't be identical, can they? Well, let's suppose we can draw some regular n-gon in this 3D lattice. This is a 2D shape, so there must exist some 2D plane which contains the regular n-gon. Also note that each vertex of the regular n-gon must have an integer coordinate. Can you see where I'm going with this? What if I just isolate the grid lines which go in one direction? Look, almost like magic, the intersection of these lines with the plane form a grid. And not just any grid, it's a grid of parallelograms. Therefore, the only regular shapes we can draw on a 3D grid are those which we can also draw on a grid of parallelograms. What's amazing about this argument is just how easily it generalizes. We just dealt with a cubic lattice, but the exact same argument works with any 3D lattice of parallelepipeds. And there was nothing special about 3D. This argument applies to any number of dimensions. There's something truly fundamental about the equilateral triangle, the square, and the regular hexagon. In any of these lattices, in any number of dimensions, these are the only shapes you'll ever be able to find. And I know what you're thinking. The numbers 3, 4, and 6. Do they appear anywhere else? Is there an even deeper connection underpinning the existence of these regular polygons? Well, the numbers 3, 4, and 6 do in fact appear somewhere else. There's a very special function which counts the number of positive integers less than or equal to some positive integer n, which share no factors with it other than 1. You may know this function. It's called Euler's totient function. Let's list out the first few values of this function. Notice something? The totient of 3, 4, and 6 seem to be the only values equal to 2. Could this just be a coincidence? Well, looks like I'm going to have to make a follow-up to this follow-up video, aren't I?